Hello. Imagine you have a function called f of x such that f of x is equal to x to the power of 2 plus 8x plus 5. And our task is to find the minimum value of f of x. If we use calculus to solve this, there is an easy way. First, we could calculate the derivative of f of x, which is 2x plus 8. And if we set f of x equal to 0, then this gives it the root for f prime, which is minus 4 for x. And this gives us a local maximum or minimum, but since we know that our function is always going high, then this is probably our local minimum. Or you can also plot this in a calculator and check it as well. So if I show this in our grid, it will look something like this. Here, this is minus 4. And also our minimum, now if we give minus 4 to our f function, it would give us 16 plus minus 32 plus 5, which is equal to minus 11. So our minimum value for this is minus 11. We showcase it here. Now we can try to show an estimate of how our function is going to look like. If we put f of 0, we will get 5, which means our f function is gonna collide with the y-axis here. And since it's symmetric, it looks something like this. Of course, my drawing is not perfect, but yes, it looks something like this. And as you can see, there are two roots, and we can find those roots based on this formula, minus b plus or equal. I can just rewrite it. Minus 8 plus minus square root of 64 minus 40, or excuse me, 20, over 2, which this is minus 8, or I can just summarize it, minus 4 plus or equal square root of 11. So you can see that these are the two places that our function collides with the x-axis. But let's say we are not going to use calculus to solve this. Let's say our function is more complicated than this, and we want to find a local or global minimum. How can we do that? Well, one way that is called genetic algorithm is to find some numbers that you think might be the answer. Or since at first we don't know anything about the problem that much, we can just generate random numbers, let's say a1, a2, a3 till an. And we don't know anything about these numbers. We just generate them, and we'll see how they do with our function. But we try to generate a lot of numbers, and also we want these numbers to be diverse. So we don't want to pick numbers that are nearly the same or close to each other. For this problem, since we can kind of estimate how the function would look, even without knowing where the local minimum is going to be, we can probably say that our minimum is going to be in a range -10 and 10. Or maybe in another problem, it is from -100 to 100. So then let's say that we want to find an answer. Then we'll generate some numbers. Let's say n is equal to 1000. And we create 1000 numbers in this range. And these are real numbers, by the way. Then, after creating them, we can evaluate how good each of our guesses are. How do we evaluate them? Well, if we use this, so we create a new sequence of numbers, which are just the original numbers, but we give them to our f function to get a new number based on our function. Then we can kind of evaluate these values. How? Well, the higher f of a is, the worse it is. And the lower f of a is, the better it actually is. So we can kind of compare two different items in our sequence. So let's say if we want to compare a of I and a of j, then we can just see how f of a of I and f a j would do compared to each other. And this is the principle that we're going to use to find a better answer each time. So how we're going to use this is we're going to sort these values based on their f function in a way that the first one, fa1, is going to be less than or equal to f of a2, then less than or equal to f of a3, less than or equal to the last one, f of an. And if we do that, it means that this is the best answer that we've got right now. This is the next one, and so on. Then we try to find a new answer based on what we currently have as our guesses. How do we do that? Well, if we have two numbers, let's say a of I and a of j, then we can kind of combine them. We can use kind of like a mean of these two to get a new number. But the thing is, if let's say f of a of I is really small and f of a of j is really big, then maybe their average would be somewhere in between, which is not that good for us. So what we can do is use a weighted average, which is something like this. We would use f of a of j over f of a of I plus f of a of j plus a of j times f of a of I over f of I plus f of a of j. Now, what this means is if f of I is smaller than f of a of j, then the probability of this is the one that we use here, by the way. This is going to be smaller. So it is more likely to pick a of I because this probability is going to be higher because f of a of j is higher. So the better the result is for one of them, the more likely it is that we are going to pick them. And the new number that we generate is going to be closer to the number that gets the better f function. And this is the principle that we're going to use. First, we came up with some guesses, and then we improved them using this function that I just this method that I just talked about to get a bit, hopefully, better results. And then we do this for a number of times, and after that we want to see how our final guess does. So for our previous problem that we had, f of x was x to the power of 2 plus 8x plus 5. So if we pick numbers from minus 10 to 10, or this range could be smaller if you know more details about the problem, or bigger if you don't know that much about the problem. But in general, you want your range to be as small as possible because you're going to generate numbers in that area. So for this problem, we estimate that it's probably going to be somewhere in this range. And let's say we pick x is equal to 0, x is equal to minus 5, x is equal to plus 7, and x is equal to minus 10. Then if we write the new sequence that we're going to get, f of 0 is going to be 5, then for minus 5 it's going to be 25 minus 40 plus 5, which is minus 10. Then for plus 7, it is going to be 49 plus 56 plus 5, which is really big. And then minus 10, it's going to be 100 minus 80 plus 5, which is 25. As you can see here, the best result that we got from these 4 guesses is the one for minus 5, which then we can sort these numbers based on the results that they get. So minus 5 comes first, then 0, then minus 10, and then at the end plus 7. Then underneath we're going to write the f functions, or as we would call it later, it's the fitness function for these numbers. But for now, the f function. So minus 10 first, then we're going to write 5, then 25, and at the end this is going to be 110, if I'm not mistaken. Then we want to kind of make new results from these. So what I'm going to do is, first of all, pick the first 2 and say that I'm going to keep these as my next guesses as well. So I would put minus 5 and 0 here. Then I want to make new guesses. So 1, I would want to merge minus 5 and 0, and maybe minus 5 and 10, minus 10, and also let's say 0 and 7, or maybe minus 10 and 7, to get some new results. So minus 5 and 0. For now, we can just use the regular average. This would give us minus 2.5. This would give us minus 7.5. And this would give us minus 3. And if we look here, you kind of want your answer to be closer to minus 4. So probably this is going to give you a smaller f. Then after this is going to be this. Then, or actually it is going to be this 5 here. After that it's going to be this, and also this maybe. And as you can see, so if we put minus 3 in our f function, we are going to get 9 plus minus 24 plus 5, which is 14 minus 24, which is minus 10, which is again the same result as minus 5. So if we kind of sort these new guesses, we are going to get something like this, minus 5, then again minus 10, and so on. But the thing is, the next time that we merge these two, we're going to get minus 4 as the average, and this is our local minimum. And this just shows that hopefully this algorithm, after several iterations, is going to get a result that we need, or at least a really good answer that is quite close to the actual solution. I'm going to also show a notebook that I wrote in Google Colab of how this algorithm actually works when we want to code it. I used Python in a notebook, and I'm going to explain how the code works and hopefully how this principle is written in code.